Hi, thanks for joining me. Today I'm going to be computing an integral using probability. We have n and k non-negative integers where k is less than or equal to n, and we want to compute this integral here. The integral from 0 to 1 of x to the k times 1 minus x to the n minus k dx. Now this integral here isn't actually too difficult to just compute manually, but I wanted to show you a really cool way to do it using probability and expected values. Let's dive right in. Okay, so we're going to begin by considering some random variables. I'm going to call them xi, and they're going to be identically and independently distributed, so IID random variables, and they're going to have the very, very common distribution of uniform over 0, 1. Okay, and this is going to be defined for I being equal to 0 all the way up to n. So there's n plus 1 of these random variables. So far, so good. Now all I'm going to do is introduce another collection of now n random variables, and these are going to be called yi. But these are going to be discrete random variables, and they can only take one of two values, either 1 or 0. And yi is going to be 1 if xi is less than x0, and it's going to be 0 if xi is bigger than x0. And this is only going to be defined for I being equal to 1 up to n. So you might wonder, well, what happens if xi equals x0? Well, thankfully, we don't really need to worry about that because this is a uniform distribution over an uncountable set. The probability that xi equals x0 is essentially 0, so I don't need to worry about it at all. So I just need to have these two collections of random variables, and now we can start to think about probabilities. So let's start with yi. What is the probability that yi equals 1? Well, you can see that it kind of depends on what x0 is. So let's suppose we know what x0 is. So let's suppose x0 equals some number x, and we want to investigate the probability that yi equals 1. Well, looking at how we've defined yi, it equals 1 when xi is less than x0. So this is equal to the probability that xi is less than x0 given x0 equals x. And now, well, we know if x0 equals x, this is just going to be the probability that xi is less than x. But because xi is a uniform random variable, the probability that xi is less than x is simply equal to x. And that's a really nice result of uniform distributions, or in particular the uniform distribution over 0, 1. Okay, so we have the probability that yi equals 1 given x0 equals x is just x. Okay, well now I can go one step further and start to think about the sums of the yi's. So what is the probability that if I add up all the yi, so y1 all the way up to yn, it equals a particular value? And now I'm going to remember the fact that k is less than or equal to n. So I'm going to put this here k, because obviously this is achievable. This is going to have a positive probability because k is less than or equal to n. And so if k of these yi's are 1 and the other ones are all 0, then this sum will definitely equal k. Okay, but again, we can see that it's going to depend on this x0. So let's suppose we know what x0 is. Let's say it's x. Okay, so what's the probability that y1 plus all the way up to yn equals k given x0 equals x? And if you've seen binomial probabilities before, you'll probably be familiar with this result, but let me try my best to explain it quickly. If we want this sum here to be equal to k, well, let's think about this. Each of these random variables, yi, can either be 1 or 0. So if we want it to add up to k, we need precisely k of them to be 1 and all the others to be 0. So let's imagine the first k are 0. So k are 1, sorry. So y1, y2, all the way up to yk. Imagine they're 1, and then yk plus 1, yk plus 2, and so on, all the way up to yn are all 0. What's the probability of that happening? Well, we need y1 to be 1, which has probability x, y2 to be 1, which has probability x, and so on all the way up to yk to be x. So that's going to have x to the k because of by independentness, or I should say independence, not independentness, made up a word there. Anyway, the last n minus k random variables, yi, all have to be 0. And now what's the probability of that happening? Well, it's got to be 1 minus x. And I've got n minus k of them, and again, by independence, I can multiply them all together, so that's going to be n minus k. But obviously, this is given, or this is assuming that the first k of these yi's are 1, and then the remaining n minus k are 0. But obviously, that doesn't need to be the case. All I need is that any collection of k of these yi's are 1, and n minus k of them are 0. So I can just multiply by the number of subsets of size k. And that has a very nice formula. It's just n choose k. And so therefore, this is our final answer. The probability that y1 plus all the way up to yn equals k, given x0 equals x, is n choose k times x to the k times 1 minus x to the n minus k. All good and well so far. So now what I'm going to do is kind of multiply both sides by 1, which seems pretty redundant, and to be honest, it kind of is. But it's just to illustrate something in just a moment. I'm going to now integrate both sides with respect to x. So if I integrate this side between 0 and 1 dx, I now get essentially the thing I'm trying to work out with this factor of n choose k, but I can bring that out in a moment. And what is this left-hand side if I integrate it between 0 and 1 dx there? Well, let's think about this. This is a conditional probability. And 1 here, the reason I wanted to multiply by 1 is because that is the probability density function of x0, because it's uniform over 0, 1. And so if I'm, by the law of conditional probability, if I integrate a conditional probability multiplied by the, the probability density function, this guy here is simply going to be the probability that y1 plus y2 plus so on plus yn equals k, which is really nice. I haven't specified what x is, so to kind of understand how I've got from here to here, if you haven't seen the law of conditional probability before, basically I've said, well, in this probability here, I'm working out the probability that y1 plus y2 plus yn, all the way up to yn, sorry, equals k, given some value of x0. And then with this integral here, I've basically said, well, let's add up, or essentially add up all those probabilities. Obviously, it's not explicitly adding up, but it's essentially saying, well, if we consider all values of x, and because all of those values of x have equal probability because of uniformness, I get this very nice result here. This is simply the probability that y1 plus y2 plus all the way up to yn equals k, and this is just n choose k times our integral that we're interested in, which maybe I'll call I. So I here is the integral from 0 to 1 of x to the k times 1 minus x to the n minus k dx. Okie dokie, so if I divide both sides by n choose k, I get that I equals 1 over n choose k times the probability that y1 plus dot 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 plus yn equals k. And now, I could leave the video there, but the real question is, what is this probability? And in fact, this isn't actually too difficult to work out. This turns out to just be 1 over n plus 1. So this is going to be 1 over n choose k times 1 over n plus 1. Why is it 1 over n plus 1? Well, I'll give you, I won't explicitly say why. I'll give you a chance to think about it. But we want the y1s plus y2 plus all the way up to yn to equal k. Let's translate back to what that means. That means that we need k of these xi's to be less than x0 and n minus k of them to be bigger than x0. And if you just think about that, that's basically saying that x0 appears in the position k plus 1. If you kind of order these n plus 1 random variables, you're basically saying that x0 occurs in position k plus 1. But obviously, the probability that x0 can be is in position k plus 1, if you order them, has to be a particular probability by symmetry. So I won't go through all the details there. I mean, I almost went through all of them there, to be honest. But I'll encourage you to put pen to paper and just see why this probability has to be 1 over n plus 1. But anyway, we've evaluated our integral I. It's 1 over n choose k times 1 over n plus 1. And obviously you can then, if you want to use the formula for n choose k to expand this or whatever, or perhaps plug in some values of n and k. But I think this is a pretty neat argument, and it does highlight the connection between probability and integration. And if you study integration at any sort of high level using kind of analysis, you'll see that there's a lot more going on behind the scenes. But I thought this was a pretty neat result, which is relatively beginner friendly. So I hope you have enjoyed this video. Anyway, if you have enjoyed it, please do give this video a like. I'd really appreciate that. And if you haven't already, please do consider subscribing. About 80% or so of people watching the videos aren't subscribed, so I'd really appreciate that as well. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.